Okay, awesome. So the first problem that I had y'all work on was the maximum depth of binary tree. And so like my approach for this was to use recursion and like essentially like you know that you want to like check for like all of the depth of all of the nodes, like travel through all of the nodes on like the left side and the right side and like compare them to each other, because like those are the places where you'd know that you'd encounter like the maximum um, number of levels. So like in this code, like my base case was that um I haven't um oh if the this just means if like the root is null, then like there are no levels, you return 0. Otherwise, I wanted to add to like a counter for that counts like the number of levels in the left side of the tree, by calling it recursively on root.left. So like it would keep going, like because I'm passing in like root.left to this function. Okay, I really should not have called like the parameter root, because that makes it so confusing, because every time I pass in something, it's like it's going to be assigned to this like variable root in like the next recursive call. But basically like it'll add 1 to each time that it calls on um, whatever is the left child of the current root, to denote that there is like at least one level there. And then like in the next call it will like continue to like add to that parameter, and it does that for both like the left and the right side, and it'll stop once it like um, reaches a leaf node. um, like that's like the return 0 that's like will eventually be added to um, like one of these calls, like either this one or this one, will like eventually reach a leaf node. And then once it does that, it'll like add 1 for each of the um, like the nodes that it traversed through in the previous recursive calls. So then like left will contain like the depth of like looking at left nodes, and then right will contain the depth of looking at like everything to the right. And then you just like compare the two and return what's greater. Does that make sense to everyone? Does anyone have questions? Okay, I'm gonna assume no. So and then the next, so this problem, the way that we solved it was like we know that like we also use recursion in this problem, and so we defined a helper function that um, is called within like the actual function is valid BST, just because we wanted like these like other parameters that like keep track of the current node that we're looking at, like a variable lower that we want like that node's value to be like we want lower to be lower than this node's value, and then we want upper to be upper than that node's value, and that's like what we're checking um, in this function. So the base case is like if there is nothing there, return true, because apparently that is like a valid binary search tree if you're like given like like a tree with nothing in it. But um, but then the other cases that we check for is So node.val is like the current node that we're looking at. So if we like, we enter it by like calling um, helper, calling the helper function on the root, and like it initializes these lower and upper parameters to lower is initialized to negative infinity, and then upper is initialized to positive infinity at first. And so then we're checking if like that value is like less than the what it's like. If the lower value is greater than this node's value, then it has to return false. Or if like the upper value is like less than that node's value, to return false, because that like doesn't make sense. Like that node should be like in between the lower and upper. And then so we do recursive calls on node.left and node.right. So node.left, we essentially want to check that like in node.left. So like imagine we were checking like this subtree. Like pretend like this actually like is supposed to be a binary search tree. Or maybe I'll just like, okay, I'm gonna pretend, I'm gonna annotate this and say like, if this is the number 2, okay, this is supposed to be a valid binary search tree. So like in this example, like if we were at this step, like we're looking at 4, like 4 is the current node. We also want to check that like its left node is like less than this 4. So like that this 3 is less than this 4. And that's like what this recursive call, like node.left, node.val, like setting the current node's value to upper and then like not changing lower, you're keeping lower the same as like the previous recursive call. So this is like make sure that like this like node.left is in between like what it's supposed to be lower than, I mean what it's supposed to be greater than, and what it's supposed to be lower than. And then this call does the same thing, except it's being called on the like the right child of the current node, so that you're like checking that again in a recursive call. And so like if you haven't returned false at like any of these steps, then like eventually you come out with the outcome that this is a valid binary search tree. Does anyone have any questions? Okay, I'm going to stop the recording and then